Welcome to the 42nd lecture in this series. So last time we talked about the Lie bracket on the general linear group GLNR and saw that the Lie bracket of left invariant vector fields corresponds to just the usual commutator of matrices AB minus BA. Now this I said that this description of the Lie bracket carries over to the subgroups ONR and SLNR. So towards the end of the lecture I made this more general statement that let G be a Lie group, H a submanifold which is closed under multiplication and inversion, then H is a Lie group. So I should add that, so this is a special, it would be natural to call H a Lie subgroup of G since it's a submanifold and a subgroup. But actually the way I defined a submanifold is somewhat restrictive, and what is generally called a Lie subgroup in the literature is something more general than this. But what I have defined is certainly a special class of Lie subgroups. And so, but for us, since we are interested in describing the Lie bracket on the subgroups, the important thing is the following, that if I start with a tangent vector at identity of in the tangent vector to H, so V belongs to tangent TEH, which is a subspace of TEG. Now this V, so in the picture let's say this is the identity and this is the vector V. This is the, let's say this is H, this is E and this is V. I can extend this V, since V is a tangent vector in both, for both H and G, I can extend it to left invariant vector fields on G, in which case I might get a vector field on the whole manifold, or I can extend it to a left invariant vector field on H. So these two are what I call XV and YV on H and G. Then the claim is that this XV, the left invariant vector field on H, is just the restriction of the left invariant vector field on G. So, and this can also be in the language of F related, this is I related. I is the inclusion map from H to G. And the proof is immediate because, if you have a map between two smooth manifolds, if M to N is a smooth map, suppose I have submanifolds S here and T here, and F actually takes this submanifold inside this. So in other words, F of S is contained in T. Then this, if I look at the derivative of F at a point in S, dfp so now there are two F's. One is, so this F I should say is F restricted to S. So let me write it more clearly. So this is F restricted to S. So in fact I can talk about two derivatives, maps of derivatives of two maps. Well, one is df restricted to S at P, and the other one is I can look at df at P and then restricted to the tangent space to S. The two will be the same. And this is immediate. One can see this. So all one has to do to see this is, basically I can either use a slice description of the submanifold, or more invariant way of doing it is to just take a realize. So I act it on to see this. You start with a tangent vector in to S. We know that every tangent vector can be realized as the derivative of a smooth curve. Let sigma from minus epsilon to S be a smooth curve with sigma 0 equals P, sigma prime 0 equals V. Then dfp acting on V is the same thing as d by dt of f composed with sigma at t equals 0. But notice that f composed, since sigma is a curve lying in S and lying entirely in S, f composed with sigma is the same thing as, I can write it as f restricted to S composed with sigma, since sigma is entirely in S. And this thing here again, using the definition of using the fact that the derivative, the action of the derivative on a tangent vector can be interpreted in terms of what it does to a smooth curve. This is the same as d of f composed with S at the point P acting on V. So this equal to this, which is what we wanted to prove. So here on the right hand side is this thing here is the same as this, and what I got on the right hand side here is the left hand side. So that's the reason why that happens. So in short, yeah, right. When I have a submanifold and I want to look at the restriction of a smooth map, I can either look at the restriction, take the derivative, or take the derivative and then just restrict it to the tangent space to the submanifold. So let's do this to left translations. So G, let's look at a left translation LP. So here I start with let P in H. So left translation, now the point is, since P is in H, left translation by P takes the subgroup back to itself. So from what we just discussed, DLP restricted to the tangent space at any point THH is the same as DLP restricted to H and then H. So if we act it on the vector V, so here I take H to be identity. So now let's take H to be identity. DEH equals D LP restricted to H of V. Now this thing here is just the restriction of Y. So this is Y, YP, and this is just YP, the left hand side, and the right hand side is just XP. So I'm just looking at left translation on H and then starting with the vector V and then pushing it all around the manifold by this derivative. So I get XP. So that proves what we wanted. So once we have this, hence, so this completes a proof of the small lemma. Hence, if H is a Lie subgroup, again Lie subgroup for us would just mean a submanifold which is also a subgroup of GLNR well, let me state the more general thing. If H is a Lie subgroup of G, V belongs to the tangent space at identity of H. Let's say V1, comma V2. I'll take two vectors. XV1, XV2, YV1, YV2 are as above. Then XV1, XV2 is nothing but the restriction of this vector field to restriction of this vector field is so in other words, if for all P in H. So in short, I can just forget about H, look at the full left invariant vector field generated by V1, and same thing for V2, which are called Y1 and YV1, YV2. Take the Lie bracket. The that Lie bracket precisely gives the Lie bracket of this smaller left invariant vector fields. And this again is the fact that this I related business. So applying hence in particular the Lie bracket on ONR and SLNR are again given by so if I start with XA, XB, the Lie bracket of XA, XB is XAB minus BA, because the point is that if I look at YA, YB in the notation we just talked about, the Lie bracket of YA, YB is given by YAB minus BA, but XAB minus AA is nothing but restriction of YAB minus BA to the subgroup, so which is XAB minus BA. So in short, if one identifies the Lie algebra, the space of left invariant vector fields with tangent spaces, with the tangent space at identity, then the Lie bracket is AB is AB minus BA. So exactly whatever happens for GLNR happens for these. Well, so that concludes our discussion. So this example is the one example which illustrates everything very clearly. Now the other thing I wanted to say before I move on to some general stuff about Lie bracket, let me again staying within the realm of matrix groups, in particular GLNR, we can also describe, we have seen what left invariant vector fields look like, we have seen what Lie brackets look like. We can also describe what integral curves look like in GLNR. So let's do that, integral curves for left invariant vector fields. Integral curves of left invariant vector fields on GLNR. So for this I need a lemma about exponential of matrices. So lemma for every A in MNR and any R greater than 0, the entries of entries of this matrix T to the power k, A to the power k by k factorial, k equal to 0 to let's say capital N, converge uniformly as n goes to infinity on the set and mod t less than r. So this here capital N, for every capital N I get a finite sum of these matrices T to the power k, A to the power k over k factorial. Now this so this will give me again an element of M and R. So I look at the n squared entries of this matrix. Each entry is so I get a sequence of functions. Actually I get n squared functions. So if I call this partial sum as Sn is equal to Snt equal to k equal to 0 to n t to the power k by k factorial, then this n squared functions Sn, the ijth entry of this T converge uniformly as n goes to infinity and mod t less than r. In this open interval, r can be as large as we want. Whatever r is on this open interval, these things converge uniformly. And therefore, so one can notice that this Sn ijt are just power series in T. So partial sums of power series for T. In other words, they just involve powers of T. So each Sn ijt is the nth partial sum of a power series in T. The good thing about power series is that if once we know that we have uniform convergence, the limit will give me a function. So again, which will depend on ij. So the limit will give me a function which I will call Sij. So we know that Sn ij, this will converge to some Sij. So again, this is a function in T. And since we have uniform convergence, this will be differentiable. Sij will be differentiable infinitely many times. And in fact, to obtain the derivatives of Sij, I can just do term by term differentiation here and take the limit. So I'll get this. So these are general facts about power series of one variable. Now, right. So now let me quickly prove the lemma. We just use the Cauchy criterion. In other words, we estimate, let us do Sn ij T minus Sm Sm ijt, and let's estimate the size of this. We want to say that when capital N and capital M are very large, this can be made small, and that very large should not depend on T. It can depend on this R, but not the specific value of T. So now let's, this will be less than, so what I'm going to do is, I'll use on MNR, we use the operator norm. So the norm of a matrix I'll define to be sup AV, and then sup AV. So here I can put V not equal to 0. So this turns out to be, this is equivalent to the Euclidean norm. So in other words, now, so let's put a O here. So this is this A now is less than or equal to there exists alpha beta such that for all A, whatever A we take, the same alpha beta will work for all A. So there's no B there, it's just A here again. So for all A, this the same alpha beta will work. So we can basically, the two norms are comparable. It's a matter of convenience. So, and it turns out that the ijth entry of a matrix, so mod Aij, the ijth entry of a matrix will be less than or equal to the full norm of a operator norm of a matrix. The Euclidean norm of the matrix here, the right hand side, what I have written here, this part is just the square root of the, you take the square all the entries of A, add them up and then take the square root. That is the Euclidean norm. Now this one is, it's a fact that Aij will be less than or equal to this. And one can see this just by acting A on certain appropriate vectors. Well, so let's use this and so write it as Sn ijt minus Sm ijt. So here I should say fix I and j, and this is the operator norm, and so which is less than or equal to, since it's a norm, triangle inequality is satisfied, and therefore I have actually sorry, so here there's no ij. I'm looking at the full matrix. Now the partial sum SNT is given by this, so I'll use triangle inequality and take the sum norm inside the sum sign. So I'll get less than or equal to summation k equals, well, assume m is bigger than n to n plus 1 to m, and then modulus of t to the power k operator norm of a 0 to the power k a operator norm of a to the power k and then I still have this k factorial. Now here is where this operator norm comes into play. So this operator norm has the nice property that norm of AB is less than or equal to norm A times norm B. That follows immediately from the definition here, and while Euclidean norm doesn't quite have this property, a constant will appear before this on the right hand side, which is not, which is not a big problem for our purposes, but this simplifies calculations. So this just turns out to be norm AB less than or equal to norm A times norm B. So if I keep using this repeatedly, then I'll get norm of AK less than or equal to norm A and the kth power of that. So this is less than or equal to n plus 1 to m modulus of t to the power k, and then I can take norm of A and then raise it to power k divided by k factorial. Well, let's call this let alpha equals mod t times norm A naught. This what I have written here, this thing is just the difference in partial sums for a new series of this time for, yeah, actually perhaps I'll stop here and just complete this the next time. Okay, thank you.